Okay, seems fine.
Yes.
Good. Okay, now coming to something a little bit relaxed. Okay, I mean a little bit relaxed thing, and that is it's not very relaxed, but it is somewhat relaxed than what we have been doing. This is something what we call as the continuous groups. Now, what can be a continuous group? Remember, in the starting phase, I said that there exist finite groups and then the infinite groups, and then infinite groups are discrete and discrete versus
Continuous.
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 Thanks. Thank you. So that is continuous. So what is a continuous group? How many elements will be there in continuous group?
Infinite.
Infinite, excellent. Countably infinite or uncountably infinite?
Uncountable.
Uncountably.
Both.
Uncountably infinite, excellent. Thank you. So I am going to now talk about those groups where there are uncountably infinite elements. Okay, maybe we are going into something which is abstract, but it is exactly opposite of that. We are going into something which is very useful in the day-to-day applications of what you have been doing. So we will come to that. So I have written something ON, SON, UN, SUN. I will explain it as we are going to proceed. So let's just continue to look at the concepts. So consider two-dimensional real space. So let's say it's a vector space, but it is in plane rather than in the 3 dimension. So where that means that my R in general is represented by XV, and of course I can write down my transpose, which is by RT. Yeah. Now, can somebody tell me what will be RT times R in this space? Regular vector space in plane. This will be what?
X square plus y square.
X.
So x square plus y square, which what we generally write as a R square, or you look into it, this is length squared. Yeah, R square is nothing but the length squared of this vector R. Yeah. Now suppose there exists, up to this point this was simple. Now suppose there exists a transformation, a linear transformation. N, okay, let's say A transformation O. And what does it do? This guy, when applied on my original vector R, gives me R prime. It's a linear transformation. It will give the vector in the same space. So, which is basically x prime y prime is O times x y. Now, can you tell me what will be the dimension of this guy O? What will be the representation of this guy O? This is a linear operator in two-dimensional space.
Two by
So,
two
what
matrix.
kind of O will be 2
Dimension.
cross 2 matrix. Yeah, I mean, remember it is a two-dimensional vector space. So you will have only two, I mean, a basis vector which is written as this xy. Yeah, so it will be nothing but a 2 cross 2 matrix. Simple things. Now, now, if I do r prime t times r prime, exactly the same thing which I did with r vector, but now r prime is nothing but a transformed vector. Oh, so what will be this guy? Follow exactly the same thing. X prime, y prime, x prime, y prime. What will be this? X prime square plus y prime square equal to r prime square, right?
Yes, sir.
Now, up to this point, my transformation is just doing it transforms. Now comes the group theory part of this. If this transformation O leaves the length squared or length invariant. Now, what do I mean to say? Let me just first say. Now comes the group part or the symmetry part. Let's consider only those transformation which leaves the length invariant. That is r dash square is equal to r square. Can you say something about the structure of this operator O or the linear transformation O? Can you say something about this?
Identity.
Okay, let's just continue. So R prime square, what is this guy? This is basically writing R prime T times R prime is equal to R T times R, right? And how R prime is related with R? OR. So what will be R prime T? Remember these are matrices 2 cross 2 and this one. So what will be R
The
prime T?
RTOT.
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 Very good. So this guy will be, that means R prime. Now look into this. R prime T is RTOT. So I have to write RTOT. And what is R prime? O times R, which is equal to RT times R. Now do you see something coming up? There is a constraint which is coming on O.
Sir, unitary.
No, we are talking about real dimensional space.
Orthogonal matrix.
Right. Remember, we are still into the real dimensional things.
Yes, sir.
So it is nothing but orthogonal matrices. Yeah. Or O is orthogonal. So what we have done, let's just revise what we have done quickly. So if we have a two-dimensional real space and we consider a transformation O which just leaves the length invariant. So there is this symmetry of this transformation O that it leaves the length invariant, that it is going to impose an interesting condition on O that this operator cannot be just any operator, but this operator has to be orthogonal. Yeah. Now, do we know any operator like this? I mean, why it's looking like an abstract concept still. Do we know any operation which leaves length invariant?
Rotation.
Okay, so let's just do that. Okay, good. So rotation in 2D space. Rotation in 2D space. So what kind of rotation I am talking about? Let's just see, think about it. So I have this, okay, x-axis and the y-axis, and I have any vector, let's say P. So this guy has the projection x and y, let's say, and I rotate my axis now. So you can think about rotating this axis y plane. So I have this new axis which is coming up. So that the rotation is, let's say, theta here. Of course, the rotation is theta here. And if I want to write down now P in terms of the rotated system, so that, okay, let's think about it. How are you going to do it? So this guy will form something x prime here, and this guy is going to form something what we call as y prime. So can you tell me how are you going to write x prime in terms of x and y? X prime. So this guy. You have one component which I am seeing that doing here, and one component going vertically up. In terms of x and y.
X is equal to x prime cos theta.
X prime is equal to, please look very carefully, and I am just going to write down x cos theta plus x prime has two component now, one in terms of x and another in terms of y. And what is the component in terms of y?
Y sin theta.
Y sin theta. What about y prime? Let me just see if you can do that. This guy y prime, this guy y prime, in terms of now x and y, and remember now theta is the angle which is with the vertical one. What
Minus
will be
x
this?
sin theta
Minus x sin theta
plus y cos theta.
plus y cos theta. So I can write down now, look into this, x prime y prime as what? Cos theta sin theta minus sin theta times and cos theta xy. Yeah, or a simple one, r prime in terms of r theta times r. Look into it. This is what is the rotation in 2D space has done. Of course, rotation is such that origin is same. I mean, you can think about a plane through the zero, and then we are rotating this axis. Now, can you figure out whether this r theta matrix obeys this property of RT times R is equal to I? Can you do it quickly? So R theta is given by this cos theta, sin theta.
Yes, sir, it obeys.
Okay, and you have got this RT theta, R theta turned out to be identity. Okay, 2 cross 2 identity, right?
Yes, sir.
Determinant of R theta?
1, sir.
1.
1. 1. Very nice. Now, what have you found? Interesting. That this guy, since it has RT times R is equal to I, this means that what rotation is going to do to R prime square? It is going to keep this.
Invariant.
Yeah, length invariant. So now you can think about it. See, I just came up with the group property. Initially, I did not talk about the rotation. I said that every time the length squared is invariant, every time length squared is invariant, we are going to have an operator which is nothing but a orthogonal operator, or the representation of the operator will be orthogonal matrix. Yeah. And now you see that the rotation in two-dimensional space enjoys that property. In fact, I can at this point go one step further. What is that step further? R is equal to R theta cos theta sin theta minus sin theta cos theta with 0 less than theta to pi. Does R form a group under composition, let's say R theta 1, R theta 2, where R theta 2 is first applied. That means I am applying first my this operator theta 2, and then I am applying this. Is it going to form a group? So how to figure out that? It has to obey how many properties?
4 property.
Four properties. So first I am stating, and then you are going to see. Remember the composition of the two, since it is the matrix representation is nothing but the matrix multiplication. You will find out that the result of this guy turns out to be theta 1 plus theta 2, which is nothing but again an element of the group R theta kind. Okay, identity element. Any rotation which leaves this system exactly the same as it was earlier.
R2 pi.
And since I am keeping 0 here and I am not keeping 2 pi, so you can say, okay, 0
R0.
or R2 pi. Okay, let's just to write it. But technically, I am just keeping 0 inside. Inverse of R theta. Any rotation which will negate the effect of the previous one, such that R theta 1 times R theta 2 is equal to R0. That is the 0 rotation.
R theta.
Oh, this should be R minus theta, which can be written as R2 pi minus theta. So apply first R theta and then apply R minus theta. Think about this. You apply first this and then you apply R minus theta. What will happen? You will get back to R0, which is nothing but the 0 rotation. Yeah, and associativity of course will hold true. You can actually check it, R theta 1, R theta 2, R theta 3, apply 3, and the ordering is not going to matter. So associativity, that also holds true. So in fact, this rotation R theta, which is represented by this 2 cross 2 matrix, and it turns out to be orthogonal one because it leaves our length invariant. This form a group under the group composition rule R theta 1 dot R theta 2. So now look into it, that where are we going? We are starting with a very generic idea that there exists some transformation O, which if it leaves the length invariant has to be an orthogonal matrix or orthogonal operator. And we find out that rotation in two-dimensional space basically enjoys everything like that. And it does not only enjoy that, but it is also going to form a group under the group composition law. So R theta does that. But now that I know this kind of a procedure, I can try to think about, does any other operation, like the way you said rotation, does any other operation in 2D space also enjoy this OT times O is equal to identity? So all I have to think about now, thinking about the possible operations, translations, rotations, and
Reflection.
reflections.
Reflection.
Now I am again not going to show you, but it is interesting that reflections about these x's can be represented by a two-dimensional matrices as well. And the only difference which you will see, that the minus sine theta which was there on the first one in the case of rotation, that has become plus, and the diagonal which were cos theta earlier, it becomes cos theta minus cos theta. It's done in a little bit tedious way, but it can be shown. But once it can be shown, you have to just check whether jt theta times j, okay, not jt, times j is this identity. If so, then it will also do the same thing what rotation has done. Exactly the same thing. That rotations form the group, reflections you will find out that also forms the group. There is a subtle difference between the two. What is the difference? Determinant of j theta.
Minus 1.
-1.
Minus 1. What was the determinant of rotation matrices?
1.
One.
Plus 1,
Plus 1.
right? So now think about it from the group structure, that I do not need to know all the transformations which will do this OT times O equal to identity. I can just keep on finding them. As soon as I find it, I will just put it under, oh, it's nothing but a group. What kind of group are we talking about? Now think about the rotation back. What kind of group are we talking about? Theta can change continuously from 0 to 2 pi. Yeah, that means the group elements which I am representing by this cos theta, sine theta, let's say minus sine theta and cos theta. How many elements are there in this group?
Finite.
In.
Right, it has infinite elements. So this is the case of continuous group. This is the case of continuous group. But there is interesting thing about this here, that all the group elements are generated by a single parameter. What is that?
Theta.
If you change that parameter, you will get a new element, which is theta. So you need only one parameter to generate all the elements of the group. And in the case of continuous groups, order of the group is still defined. Earlier order of the group was exactly the number of elements, but order of the continuous group, which is represented by a rotation, which is represented by a reflection, that is nothing but number of independent parameter required to generate the group. And in this case, it is just one. So we will call order of the continuous group rotation nothing but 1. Order of the continuous group reflection nothing but 1. In fact, at this time, I can generalize whatever I have done, that O2, which is nothing but orthogonal orthogonal 2 cross 2 matrices under matrix multiplication forms a group. Very interesting. So I have now come up with this something called O2. What is O in that? O is orthogonal. What is 2 in that? 2 is nothing but 2 cross 2 matrices, which I have represented in this case for say rotation matrices, reflection matrices, or in fact I can ask you to find out A, B, C, D, where A, B, C, D are all real. O2, which is given by A, B, C, D, where O2 enjoys this property, give the idea of what kind of element constraints are there. What are the constraints on A, B, C, and D? Can you just quickly found out OTO equal to I? Yeah, kindly bear with me. I will go a little bit longer, but I just want to wrap up this concept here. So OTO is equal to I, which is or OT. I mean, do whatever. What is OT? This will be A, C, B, D, right? I mean, this is as simple as that. So what will be the
A
first
square
term?
plus C square is equal to 1.
Yeah, that is coming out. Okay.
AB plus CD is equal to 0.
AP plus CD equal to 0. So that will come out from there. And then here.
BA plus DC.
So AB plus CD, basically A and B are A, B, C, D are all real numbers.
And B square plus D square.
B square plus D square. Yeah, and you could have done it OT, O times OT, and you would have got AC plus BD as well. I mean, in these places, but it is fine. See the constraints which are coming up. A square plus A and C cannot be any general element. A and C are the elements such that A square plus C square has to be equal to 1. B square plus D square has to be equal to 1. So constraints like this will come on A, B, C, D. Not only that, there is another constraint which will come. What will be the determinant of O? Determinant of orthogonal matrices.
AD minus BC is equal to 1.
Up to certain point you are right, except that determinant of O can be plus and
Plus
minus 1, right? Up to certain point, I mean plus 1 was right, but it can also have, yeah, this is the property of the orthogonal matrices, nothing beyond that. So what we have come up with from our example which we started with, that length squared invariant or the length invariant under a transformation represents orthogonal matrices in two-dimensional spaces. Now that we know that, that means that whatever the properties of the orthogonal matrices we know, and it's very similar to unitary matrices also. I mean, the rows and the columns will also form the normalized vectors, things like those, along with this determinant O equal to plus minus 1. So set of orthogonal 2 cross 2 matrices under matrix multiplication forms a group. Once people start thinking about it, then people can start thinking about, let's just try to figure out what are the physical transformations which are doing it. We know if we find out any matrix of the kind R theta or J theta, they are going to form groups. So O2 is one continuous group. What will be the order of this group?
1.
Order of the group is exactly 1. In fact, I can ask you later on to figure out that this is something which we are going to do. For n is equal to 2, you will find out that n square minus n plus 1 n over 2. This is the constraints which we have. So these are the number of elements, 4, 2 into 2. N is 2. What will be this number which will come if you put n is equal to 2? 4 minus
3.
3, this will come out to be 1. So order of the group will be defined by this. N square, which is nothing but A, B, C and D, 4 parameters which are there to begin with, and the number of constraints which are there, which is n into n plus 1 over 2 in this system, which 3 constraints which are coming. Remember the constraints which are coming here: a square plus c square, b square plus d square, and then this ab plus cd. The other constraint, the fourth one, is same as the the third constraint, which you will get. So this is how generally one figures out the order of the group. It's a O2 is a continuous group of order 1. That's the important thing which we are carrying forward. There exists this, and the last thing which I just wanted to tell you, last thing for this class, that O2 can be further SO2. O is orthogonal, 2 is 2 cross 2 matrices, and this S is something special which we call as proper rotation like property. And what will be this property? That the determinant of this SO2 will be equal to exactly plus 1. So O2, which enjoys the property that determinant can be plus minus 1, there exists something what is a smaller than that, that is we are going to choose just determinant equal to plus 1. And remember that it corresponds to rotation, and reflection is something else, so we are just skipping it out. This SO2 forms a subgroup of O2, and it has the same order, which is 1. It is a continuous group, and I will just stop here, let you ask question, and then we will meet at 2 to further carry out our analysis. So what I have done, very quickly revisit, that we came up with the idea of the continuous groups. And here I gave you one example, that let's consider the set of transformations which leaves the length invariant. And we say that there are physical cases for that, rotations, reflections, they are all like that. They all form actually the group. In fact, the property which is enjoyed at the higher level is that set of orthogonal 2 cross 2 matrices under matrix multiplication forms a group. It's a continuous group because the parameter can be continuously changed to generate the group elements, and it will have order 1. That means that you will require only one element to generate the entire group. At this point, I will stop, let you ask questions. Okay, by the way, I could have given you as in the first question in the group theory examples. Can you figure out whether 2 cross 2 orthogonal matrices form a group? And this is basically what we are doing right now. Except that now I am telling you this is very important in case of the continuous ones. Okay, so we'll meet at 2 and then you will ask questions there. And look at the example, by the way. Afghan ka example mat chhodna bhai. It's important. Good. Okay, see
All
you.
right, sir. Thank you.
Thank you, sir.
Okay,
Yep. Oh, too many sentences coming together. Can you just utter one sentence at a time? Hello? Am I audible?
Yes, sir, you're audible.
Okay, I am. So somebody else